Hello everyone, welcome back to another lecture of chemical process design and simulations. And as you know, there are four CLOs of this course. Number one is related to the fundamentals, number two is related to simulation, three is related to analysis, and four is related to design. And as you know, after S2, we are now moving towards Aspen Energy Analyzer, and we will design heat exchanger networks using Aspen Energy Analyzer. But before starting this, let's look back at the example which we have done before S2 examination. Cold stream, whose mass flow rate is 0.25 kg per second with a specific heat capacity of 4 kilojoule per kg Kelvin, with a heat capacity flow rate which is calculated by multiplying these two terms, which is 1 is entering at 20 degrees centigrade, which is the supply temperature, and the target temperature is 200 degrees centigrade with a heat load of 180 kilowatt. And for hot stream, it is at 150 degrees centigrade inlet, 50 outlet, 1.8 heat capacity flow rate, and a heat load of 180 kilowatt. And by graphical method, for a temperature difference of 20 degrees centigrade, we had drawn this diagram in our class activity, and we had computed that the heating duty requirement is 70 kilowatt and the cooling duty requirement is 70 kilowatt with a heat recovery of 110 kilowatt. And for the problem table approach, if I take you to the final side, if you remember that 140 was our pinch temperature, 70 kilowatt was heating utility, 70 kilowatt was cooling utility. This was the overall procedure which has been shown to you, and these were the results of the system. Hot pitch temperature was 150 degrees centigrade, cold pitch temperature 130 degrees centigrade, hot utility and cold utility 70 kilowatt each. And then we had designed the heat exchanger network in our lecture number 27, where we had first divided the system into above pinch and below pinch. And as you see that there is no hot stream above pinch, and we follow the rule that first we check that number of hot stream should be less than or equal to number of cold stream. Obviously there is one cold stream. Then we check the CP, obviously once there is no hot stream involved, so we can simply place heat exchanger which is the related to utility of 70 kilowatt. And then there was a heat exchanger which was installed between the stream number 2, which is the hot stream, and stream number 1, which is the cold stream, after following the rules below pinch. This is the calculation of it: 88.89 degrees centigrade, and then a cold utility requirement of 70 kilowatt. And this whole system is for delta T minimum of 20 degrees centigrade. Obviously, once you change the value of delta T minimum, the answers or the utility requirements and the pinch temperatures will be different. So now we will move to the Aspen Energy Analyzer. But before moving to Aspen Energy Analyzer, we have to read some basics of it as well. So it performs heat integration functionality through two means through heat integration case and heat integration project. Now, what is the difference between the case and the project? The heat integration case is limited with one scenario and one design, while the heat integration project is linked with multiple scenarios, and each scenario could have multiple design. It means there is on at a time only one design in heat integration case, while in project there could be more than one designs and more than one scenarios as well. So heat integration case is useful for those users who want to perform a quick energy analysis, or for those who want to study current plant operation, while this is more suitable for the users who want to make structured modifications and compare these modifications, and useful for revamp studies. So this is the basic difference between the case and the project, and obviously we will be going towards the case in this first example of Aspen Energy Analyzer. So let's quickly move to Aspen Energy Analyzer and design a heat exchanger network using heat integration case. Obviously, we are not interested in the scenarios in this course, but we are interested in single scenario and single design at a time for this course. So once you open, you find this interface which is blank. This is new case, open, save case, heat integration manager. I will come back at it later. Heat integration case, create new heat integration case, and create new heat integration project. So basically, the heat integration manager contains both of them. If you click at heat integration, it asks either you want to create heat integration case or project, or the cases which you have already generated or saved, which These will appear in all heat integration. If you want to generate heat integration case, click on it and add it. This is one way of doing it. The other way of doing it is directly click heat integration case. So same goes for heat integration project. Now expand it. Data transfer from Aspen Hysys. You can transfer data from Aspen Hysys directly over here if the format is same. Similarly, if you want to transfer it from Aspen Plus, you can do it as well. From Excel, you can do it as well. Now this is open targets view. As you can see, heating requirement, cooling requirement, minimum number of targets for total minimum, MER, shells, then area targets, cost index, and pinch temperatures. Then utility targets, range targets, plots table. This is the overall first introduction. We will see its functionality right now. And then delta T minimum value you specify here. There is no other point in it. Then if you want to see the composite curve, you can see it here. Grand composite curve, similarly utility composite curve. And then this tab, we will open it for heat exchanger grid diagram. Here we will design a heat exchanger network, HE and heat exchanger network. But now our first task is to enter the data. As you can see, it is blue and there is no other option over here. So what we need to do, we need to first specify the name of the stream. Once we specify the name, then we can enter other parameters. Like if I take you back and type any other thing, 120, 130, or even 123, nothing will be typed over here because your first task, as always, will be to specify the stream number. And once you specified it, as you can see, everything is now opened up and you can enter your data. So I will first specify the hot stream whose inlet temperature is 150 degrees centigrade. Even you can change the temperature over here as per your convenience. And outlet temperature is 50 degrees centigrade. And this is now labeled as red. It means it is a hot stream. Now, once you have specified a hot stream, you cannot change this to cold stream. Let me do it like 30 to 50. It won't change. Once you have specified it as a cold stream or a hot stream, it will remain as it is. You cannot change. So be careful while specifying it. Now you can either specify MCP. Obviously, we have the value of MCP as well. And you can specify the enthalpy. So I'm going to specify enthalpy of 180 kilowatt. There is no need of giving minus plus. One will take it like that. कि Aspen इसको खुद ही adjust करेगा. आपको minus plus देने की कोई जरूरत नहीं है. This is the overall heat transfer coefficient. It is for water. Since we do not know the medium of it, so we will click it at default. There are other options as well: gasoline, fuel oil, heavy oil. If you know the components which are involved during the heat exchange, then you can specify. Otherwise, you can simply click on default. So it will be at default. This is the minimum information requirement. If you want to specify flow rate, effective CP, and DT constant, it's up to you, but there is no need of it. Now specify the stream number 2, and it is from 20 to 200 degrees centigrade, and it is a cold stream. And again, the heat load or the enthalpy is 180 kilowatt. Now, if you click here, you can see now there are options available over here. Heating utility 60 kilowatt, cooling utility 60 kilowatt, but this is for a temperature difference of 10 degrees centigrade and you have to specify it as 20. Now 70 kilowatt heating utility energy target, 70 kilowatt cooling utility, hot pinch temperature 150, 130 cold pinch temperature. These are the initial calculations, or you can see the current setup, as you can see, is of the problem table approach or the graphical method from which you have computed these values. Now, if I take you to the plots or tables, you can see this is the utility composite curve. If you want to see the composite curve, this is the same composite curve which you had drawn in the class activity, the grand composite curve of it as well, and there are multiple options as well. And if you want to vary the delta T minimum, means if you want to give the range of delta T minimum from let's say 5 to 20 with an interval of 1 and ask it to calculate. So it is just now calculating and it will give you an answer of cost or anything else. Like it will give you an answer of that with the increasing delta T minimum, the hot utility is increasing. With the increasing delta T minimum, the cold utility is increasing. However, it is not giving any information about the cost. Why? Because currently there is no information about cost over here as well. Now, how we can compute that information? For this, we need to specify the utility because if you see the heating is insufficient, the cooling is insufficient because You have just defined the streams, process streams, but you have not specified the utilities. So how you can specify utility? Going here to utility streams. In process streams, you have specified the process streams. This is the hot stream, this is the cold stream. But now you have to go to utility stream. And for cold utility, usually we prefer water. So there are a lot of options available over here: steam, heat, very high temperature, refrigerant, cooling water, air, and so on. So we will select cooling water. And once you have specified the cooling water, you can see the cold is sufficient. And this is the by default temperatures. You can, even if you are given the temperatures, for example, you have been given that cooling water should enter at 32 degrees centigrade and leave at 35 degrees centigrade. So it will adjust accordingly. And let me say that LP steam is sufficient. Let me select it and see whether hot utility is sufficient or not. So as you can see, hot utility is not sufficient for this. So I have to change it to MP steam and see whether it is sufficient or not. It is still not sufficient. And if I take it to HP stream, it is now sufficient. So that's how you can manipulate the utilities, or even you can manipulate the temperatures. So now coming back, and you can see heating is sufficient, cooling is sufficient, and you are now getting the results of area. You are now getting the results of cost. You know that there are minimum of 3 units which are required for this whole setup, with shells as 5. Minimum for MER, maximum energy recovery. So that are 3. And how many you have designed in your lecture? There were 3. So once after doing it, if you can want to go back and again you want to calculate it, so you can see the graph will be generated like this for 5 to 15 and so on degrees centigrade. And similarly, if you want to see the composite curve, you can see over here as well. If you want to see the grand composite curve, it is available over here as well. And if you want to see utility composite curve, it is available over here as well. Now, before going to this heat exchanger network diagram, you can go to this economics and you can see that there are parameters specified over here. That rate of return is 10%, plant life 5 years, annualization factor is calculated by this formula, hours of operation, these are usually constant. A, B, and C values for this heat exchanger are given as well. If you want to specify the fired heater, you can also specify it as well over here. So these calculations will be used, and how these can be calculated: at capital cost index, this A plus B heat exchanger area over shells. The area is calculated as I have shown you over shells raised to power C multiplied by shells. So this is how the cost is calculated for the system. As you can see over here that the capital cost, operating cost, and total annual costs are calculated. So once after doing it, this part is currently related to the problem table approach, graphical method, and one new thing you have learned, that you have specified the utilities, and for particular utilities, you have calculated the area and cost. Obviously, once you change the utility, these costs will change. So you have to see that which of the utility is the best in the system. Obviously, if you want to use air, water, and refrigerant, just select these and see the effect on the area requirements as well. Once we click it, and we have a new window opened. So once I will click it and I will show these side by side for better representation like this. So as you know, this is a pinched problem. This is not a threshold problem. For a threshold problem, there is no requirement of above and below pinch of, because obviously there is no pinch temperature for threshold. But for a pinch problem, first we need to specify, or first we need to divide this problem into above and below pinch. And how we can divide it, I will show you in a moment. You can add heat exchanger by clicking here. If you want to do stream splitting, you can click here. If you want to do the optimization, click here. Controllability view, then view capital and energy targets. We will come at this point, and this is the one of the important point, because initially these have been calculated, and we have to see whether we have calculated correctly. Means we had calculated area here as 500 square meter, and here it is calculated as 510 square meter. So it means we have exceeded it. This would be 105% या 106% होगा, यानी हमने थोड़ा उसका एरिया एक्सीड कर दिया है. तो इसका मतलब है कि हमें कहीं इंप्रूवमेंट की जरूरत है, या ये इतना ही रहेगा. तो ये हमें थोड़ा सा उसके बारे में भी बता देता है कि आपको कहाँ कहाँ इंप्रूवमेंट की जरूरत हो सकती है. And then network performance, cost, again important parameter in it. Then driving force plot, bar chart, cross pinch load, if there is some cross pinch happening in the system or not. And obviously we know the three golden rules, that we cannot transfer heat across the pinch, we cannot use cold utility above pinch and hot utility below pinch. And then unsatisfied stream, switch stream directions. If you want to switch it, you can do it as well. And this is how we can draw the pinch lines, the show height pinch lines. If you click it, the pinch line will appear. And as you can see, this is the same network diagram which we have drawn manually. And what we need to do now, at above pinch there is no hot stream, so what we need to do now, click it. It is not like that, just simply you click it and it will be selected. Right click it and place it, and then click here, line, and connect it. So this is the tricky method, but you have to learn this method as well. Now double click on it. Inlet temperature of hot utility is 250, outlet temperature is 240, and this is fixed. You cannot vary it. Now this stream here it at 130 degrees centigrade. This temperature of 20 is here, but obviously you are concerned with the inlet temperature. If you see, this is a heat exchanger. The inlet temperature here is 130 degrees centigrade. The outlet temperature here is 200 degrees centigrade. So we have to specify it here as 130 degrees centigrade. And once we want to completely heat exchange with it, कि हम चाहते हैं कि पूरा का पूरा 200 पे जाए, so we can do it in the two ways, like either tide it, so it will be from 130 to 200 degrees centigrade, or simply tide it 200, so both values are same. So that's how the heat exchanger network design has been carried out. And you can see the duty requirement is 70 kilowatt for it, and 4.554 square meter heat exchanger area is required for the heat exchange between these two streams. One of these is a process stream which is going from 130 to 200 degrees centigrade. Another one is the HP stream 250 to 249 degrees centigrade. Now we want to heat exchange between these two streams. What we need to do, obviously, just like this, place a heat exchanger, then simply click it and drag it. No need to worry, just double click on it. Now, if you see that, and if you remember your concepts of heat exchanger design, that all the cold process stream will get heat, or its heat exchange will be complete, but there will be a hot stream whose heat will remain. Obviously, you are more concerned that what will be the temperatures. If you tide it, it will be 150. If you tide it, it will be 20. That here inlet temperature is 20, here inlet temperature is 150. Now you are concerned what would be the outlet temperatures. Whether should I tide it or not? Let me see. If I tide it, you can see it has moved to 200 degrees centigrade. While here the requirement is 130 degrees centigrade. So it means that this connection is not correct. Now remove it and tide it. And as you can see, 88.89 degrees centigrade, which we had calculated manually. So this value is the same, and the cold stream is now completed. Partially it has exchanged heat with the hot stream, and partially with the hot utility. And now for the remaining portion, what we will do, we will click, place it over here and click here. So as you can, there is no hard and fast rule that you have to place exchanger here. You can place exchanger over here. So you have to place on one of them and then draw a line between these two. So double click on it, tide it, and you can see the overall system has been completed. And once this bar is green, it shows the design has been completed successfully. And infeasible heat exchanger 0, heat exchanger not calculated 0, all the heat exchangers have been calculated. There is no unsatisfied stream in the system. And this is the same system, the same representation which you had done here as well. So you can see you have calculated it successfully. Now our next task, which obviously we hadn't discussed during the handwritten calculations, was to check whether we have done it correctly or not, whether we have not specified it or over specified it. Number of units are 3, total area 47.1 square meter. These are the values of indexes. Then we will check the network performance, and as you can see, the heating utility percentage of target is 100, means the heating utility which was calculated actually over here 70 kilowatt is the same which we have computed from the heat exchanger network design. Similarly, cooling utility is 70 kilowatt, number of units requirement 3, number of shells requirement 5, obviously here it is 5, and total area requirement is 47.14. Well, it was somewhat 47.1, but it is 99.99%. Means we have remained within the targets. We have not exceeded above 100%. So the things which we had computed from the previous design, or like from the initial estimation, are the same as we have computed from the heat exchanger network design. And if you talk about the cost, you can see actually you have saved some cost. Like here it was predicted that 5.408 multiplied by 10 raised to power 4 will be the cost. Well, here it is 5.389 multiplied by 10 raised to power 4. And similarly, here it is 6.407, and here it was computed was 6.423. So actually, you have saved the cost, or you have designed it in a better way. So that's how you do the heat exchanger network design using Aspen Energy Analyzer. This was our first example. I would suggest you to do the same example as we have discussed in our lecture number 24, and that was also related to the two stream problem. So it will be easy for you guys to have an understanding of the Aspen Energy Analyzer. Till then, it's goodbye.